Okay, let's unpack this. Imagine it's just a regular day in Yungay, Peru.
Right.
This town, right, it's nestled below this huge mountain, the Huascaran.
Right.
Then, boom, an earthquake hits, shakes the whole region. But what happens next is, well, it's almost unbelievable.
Yeah.
A massive slab of glacial ice, like 800 meters wide, just shears off the mountain.
Huge, just enormous.
Think about that. It falls over 3.7 kilometers, picking up insane speed.
Yeah.
Over 300 kilometers an hour.
Faster than a race car.
Exactly. And as it comes down, it scoops up rock, soil, turns into this churning slurry, 50 million cubic meters of mud and debris.
Just a colossal amount of material.
And it travels another 14.5 kilometers in less than 4 minutes. I mean, that's incredibly fast.
Unimaginably fast.
Apparently, part of it even rode on compressed air for a bit, which is wild. Left some grass untouched, then just obliterated the town. Yungay vanished.
Buried under meters of mud.
Over 18,000 people gone. Just like that. You can only see the tops of the church, a few trees. It's just brutal proof the ground under our feet isn't always solid.
It really isn't. And Yungay, it's such a stark reminder, isn't it, that even land that looks completely stable, if it's on a slope, gravity is always at work.
Constantly pulling.
Constantly. Pulling rock, loose stuff, what we call regolith snow, ice. Everything wants to go downhill. And geologists, we call this whole process mass movement. Or sometimes mass wasting.
Mass wasting, okay.
And the tragedy of Yungay really highlights the incredible sudden power involved. And, you know, the thing is, our sources point out it wasn't entirely out of the blue.
Really?
Yeah, Yungay was actually built on debris from previous landslides. That history was a warning sign, a really serious one, sadly missed.
Wow. Okay, so for this deep dive, we're really getting into this whole topic of mass movements. It's fascinating, but yeah, sometimes pretty terrifying.
It can be.
We'll look at all the different kinds. From the ones that are so slow you barely notice, the ones that hit with devastating speed. We'll dig into the forces involved, maybe even look underwater. You mentioned submarine stuff.
Absolutely. There's evidence down there, too, and connections to things like tsunamis.
Right. And we'll talk about triggers, what sets these things off, and which places are most at risk. The goal here is to give you, our listener, a really solid understanding of these powerful geological events and, you know, how we try to deal with them.
And it's useful right at the start to clarify some terms. We all say landslide or avalanche, but geologists and engineers, we're a bit more specific.
Okay, how so?
Well, we classify mass movements based on a few key things. First, the material, is it solid rock or loose stuff like regolith or snow or ice?
Makes sense.
Second, the velocity. How fast is it moving? Super slow, kind of medium, or really fast?
Okay.
Then, the character of the movement. Does it hold together as one block, or does it break up into a messy jumble? Is it wet or dry?
Right.
And finally, the environment. Is it happening on land, subaerial, or underwater submarine? Getting these details right helps us figure out the mechanics and the potential danger.
All right, let's start with the slow ones then. The ones that sneak up on you. You mentioned creep.
Yeah, creep. It's exactly what it sounds like, this incredibly slow, steady downhill movement of regolith. Soil, loose rock fragments, that kind of thing.
How does that even happen if it's so slow?
It's all about cycles of expansion and contraction. So think about freezing and thawing or wetting and drying. When the ground freezes or gets wet, it expands a tiny bit, pushing particles outwards, sort of perpendicular to the slope.
Okay.
Then when it thaws or dries, it contracts. But gravity pulls those particles straight down, so they end up just a tiny bit further downslope than where they started.
Ah, I see. So each cycle is just a minuscule shift downhill.
Exactly. It's imperceptible day to day, but over years, decades, it adds up. You won't see creep happening, but you often see the results.
Like what? What should you look for?
Well, the classic sign is tilted trees with the curved bases. The tree tries to grow straight up, but the ground is slowly moving out from under its base.
So the trunk curves upwards.
Right. You also see tilted fences, gravestones leaning over, retaining walls bulging out, maybe even cracks or sagging in building foundations. It's all evidence of that slow, relentless downhill movement.
So even solid-looking ground can be moving beneath us. Wow.
It's a reminder that stability isn't always permanent.
Okay, what other slow ones are there? Solifluction, that sounds specific.
It is. Solifluction happens mainly in Arctic areas or way up high in mountains where you have permafrost.
Ground that's frozen solid year-round, deep down.
Exactly. So in the summer, only the top layer thaws out, but the water from that thaw can't drain downwards because of the frozen permafrost below.
Ah, so the top layer gets waterlogged.
Completely saturated. And it loses its strength, basically turns into this wet mush that slowly flows downhill in sheets or lobes. You see it a lot in cold tundra landscapes.
Okay. And rock glaciers. That sounds like a contradiction.
Yeah, it does a bit, but they're real. A rock glacier is mostly rock fragments, pebbles, boulders, all sorts, but they're cemented together by ice in the gaps between the rocks.
So it's like icy rubble.
Pretty much. And even though it's mostly rock, the ice inside allows the whole mass to deform and flow slowly downhill, kind of like a real glacier, but much slower.
How do they form?
Two main ways, really. Either snow and melt water seep into rock debris that's sitting on top of permafrost and then freeze, locking it all together. Or you can have a regular glacier that picks up a ton of rock debris on top, and then as the main ice melts away, it leaves behind this rock-rich mass held together by the remaining interstitial ice.
And you can tell they're flowing.
Yeah, they often have this wrinkled or ridged surface. That's a dead giveaway that the whole thing is slowly moving downhill due to the ice inside.
Fascinating. Okay, so those are the slow movers. What about the ones in the middle? Intermediate speed. I remember reading about slumps. Something about a highway in California.
Ah, yes, slumps. And the Pacific Palisades Highway 1 example is a good one. So a slump is when a block of rock or regolith moves downslope, but it stays relatively coherent, at least initially.
Like a chunk sliding down.
Sort of, yeah. And it moves along a curved failure surface, shaped kind of like a spoon. Imagine souping out part of a hillside. The surface left behind is like the failure surface.
Okay.
At the top, you get this steep cliff face, often curved, called the headscarp. That's where the block broke away. And at the bottom, the material piles up into what we call the toe.
And the block itself, does it stay in one piece?
Sometimes it does, but often it breaks into smaller slices as it moves, tilting backwards a bit. And yeah, that 1958 slide on Highway 1, a big section of the road just gradually shifted and sank over days. That was a slump.
And heavy rain can trigger these.
Definitely. Like those slides in New York State our sources mention. When the ground gets saturated, it gets heavier and the failure surface can get weaker or more slippery. Structures built on or across a slump zone are really vulnerable. They crack, tilt, get pulled apart.
Right. Then we have mud flows and debris flows. Those sound messier.
And faster.
Much messier, and often much faster, yes. This happens when regolith gets completely saturated with water and turns into this thick, viscous slurry.
Like wet concrete.
Kinda, yeah. If it's mostly fine stuff like silt and clay, we call it a mud flow or mudslide. If it has lots of bigger bits mixed in pebbles, rocks, even boulders, it's a debris flow.
What usually causes them?
Heavy rainfall is the big one, especially on steep slopes with lots of loose material, like weathered rock or unconsolidated soil. Think about those hillsides in Rio de Janeiro where people build shacks.
Very vulnerable.
Tragically so. And it's not just tropical areas. Remember the Oso mudslide in Washington State back in 2014?
Oh, yeah, that was awful. 44 people.
A terrible reminder. And the speed depends a lot on how much water there is and how steep the slope is. They can get incredibly fast, over 100 kilometers an hour sometimes.
Wow.
And because they're so dense and thick, they can carry huge things, cars, trees, even whole houses. They tend to follow existing channels like stream valleys and then spread out at the bottom, burying everything.
And there's a volcanic version too, right? Lahars. Exactly. Lahars are specifically volcanic mud flows or debris flows. They form when volcanic ash and other loose stuff from an eruption mixes with water.
Where does the water come from?
Could be melting snow and ice from the volcano's heat, or heavy rain falling on fresh ash deposits, or even water bursting out from a crater lake.
And they can be just as devastating.
Oh, absolutely. The 1985 Armero disaster in Colombia, a lahar from the Nevado del Ruiz volcano wiped out the town. Something like 20,000 people died. Just horrific. Shows the immense danger these volcanic flows pose.
Okay, moving up the speed scale again.
Yeah.
To the really fast movements. Rock slides and debris slides.
Right. These are sudden. A big chunk of rock slide, or mostly regolith, a debris slide, breaks loose from a steep slope and slides rapidly downhill.
What does this slide on?
Usually on a pre-existing weak surface. Could be a fault, a set of joints, or maybe a weak layer of rock, like shale, especially if that layer is tilted parallel to the slope.
And they move fast.
Very fast, sometimes up to 300 kilometers an hour. As they move, they often break apart into just a chaotic jumble of debris.
How can they go that fast?
Sometimes they trap a cushion of air underneath them as they slide. That reduces friction, lets them really accelerate.
Wow. Any major examples?
The Vaiont Dam disaster in Italy, 1963, that's a textbook tragic example of a rock slide. A massive wedge of rock on Monte Toc above the reservoir.
And just let go.
Yeah. There were weak shale layers underneath, dipping towards the reservoir. About 600 million tons of rock suddenly slid into the water.
Into the reservoir behind the dam.
Exactly. Displaced a huge amount of water, sent a giant wave over the dam wall. It completely destroyed the town of Longarone downstream. Around 1,500 people killed. A catastrophic failure to recognize the geological risk.
Unbelievable. Okay, then avalanches. We usually think of snow.
And that's the common meaning, for sure.
Hmm.
Like the 1999 Austrian Alps avalanche that hit that resort, a massive flow of snow.
Are there different kinds of snow avalanches?
Broadly, yes. You have wet snow avalanches, they're denser, flow more like a slurry. And dry snow avalanches, they're these turbulent clouds of powder snow mixed with air, and they can be incredibly fast.
What sets them off?
Often things like a cornice collapsing that's an overhanging drift of snow on a ridge, or a whole slab of snow breaking loose along a weak layer within the snowpack. Sometimes just a loud noise, or skier.
And they follow specific paths.
Often, yeah. Down gullies or slopes known as avalanche chutes. It's why ski patrols and road crews sometimes use explosives to trigger smaller, controlled avalanches to prevent a huge, dangerous one from building up.
But you said the term avalanche is broader in geology.
It is. Geologists use avalanche to describe any really fast, turbulent flow where solid particles are mixed with it could be air, could be water. So you can have debris avalanches, which are fast flows of rock and soil and air, or even submarine avalanches underwater.
Ah, okay, like density currents.
Exactly. The mixture of solids and fluid is denser than the surrounding fluid, so it flows rapidly downhill or downslope because of gravity.
Got it. And the last fast ones are rockfalls and debris falls. These sound simpler.
They are, fundamentally. It's just rock, or a mass of rock, rockfall, or regolith debris fall detaching from a cliff or steep slope and falling pretty much straight down through the air.
Just gravity pulling it off the edge.
Right. Often happens along joints or fractures in the rock face. Sometimes it's just a few rocks, but they can be enormous. Like the Alm Rockfall in Switzerland in 1881, 10 million cubic meters of rock came down, buried the village.
Wow. And where does the debris end up?
It piles up at the bottom of the cliff in a sloping heap called a talus slope, and really big, fast rockfalls can actually create a powerful blast of wind as they displace the air. They've seen that in Yosemite.
A wind blast from falling rocks.
Yeah, and sadly, smaller rockfalls and debris falls are pretty common along road cuts, where digging has destabilized the slope.
Okay, so that covers the main types on land. But you mentioned things happening underwater, too. Submarine mass movements.
Yes, gravity doesn't stop at the coast. And what's really interesting is that these underwater events often leave behind really clear evidence in the sediment layers on the seafloor. We can study them long after they happened.
So what kinds of things do you see down there?
Well, you get submarine slumps, similar to on land, where blocks of sediment slide downslope but stay relatively intact, just folding and contorting the layers beneath them, like
Right.
wrinkling a tablecloth.
Okay.
Then you have submarine debris, flows the mass, breaks apart into a messy, slurry, big chunks mixed in with mud, flowing downslope.
And turbidity currents, those sound different.
They are. A turbidity current is when sediment gets mixed up with water, creating this dense, turbulent cloud that's heavier than the surrounding seawater, so it rushes downslope.
Where do they happen?
Often down submarine canyons, carving them out even deeper as they go. When the current eventually slows down, the sediment settles out in a specific way.
How so?
It forms graded beds. The heaviest, coarsest particles settle first, then progressively finer stuff on top. It's a characteristic signature. You can even simulate these in lab tanks.
And these underwater events can be huge.
Absolutely enormous. Seafloor mapping using things like sonar has revealed gigantic submarine landslides, especially around volcanic islands like Hawaii or along active tectonic plate boundaries.
You see the stars.
Yeah, these huge scallop-shaped bites taken out of the underwater slope. Some slumps are hundreds of kilometers long. The steep cliffs you see on some islands might actually be the head scarps of these massive underwater failures.
Wow. And it happens on quieter coasts, too.
Yes, even on passive margins like the Atlantic coast, there's evidence of large-scale slumping over geological time.
And this connects to tsunamis, right? How does that work?
It's all about water displacement. If a large enough mass of sediment suddenly slides or slumps on the seafloor, it pushes the water above it upwards. That creates a bulge on the sea surface that propagates outwards as a tsunami wave.
So an underwater landslide can trigger a tsunami, just like an earthquake can.
Exactly. The 1998 Papua New Guinea event is a tragic example. An earthquake likely triggered a big submarine slump offshore, and that slump generated the deadly tsunami that hit the coast.
And this has happened before, historically.
Oh, yes. Geological evidence points to massive prehistoric tsunamis caused by submarine slides. The Storegga slide off the coast of Norway happened thousands of years ago. It was huge,
And it caused tsunamis.
believed to have sent tsunamis crashing into coastlines all around the North Sea. They find evidence like smashed seashells deposited way inland in Scotland and Norway.
What other kinds of evidence point to past tsunamis?
You might find giant boulders tossed far inland, layers of sand and gravel deposited high above normal sea level, or cliffs that look eroded way up high beyond where normal storm waves could reach.
Okay, fascinating and scary stuff. So we know what these mass movements are. Let's talk about why they happen. What are the basic conditions needed?
Well, our sources really point to three main preconditions. First, the material on the slope, the rock, or the regolith, has to be weakened somehow, fracturing, weathering, that kind of thing.
Right, it needs to be breakable.
Second, you obviously need relief. You need a slope for gravity to pull things down. No slope, no mass movement.
Makes sense.
And third, there's usually some kind of trigger, an event that finally pushes the slope over the edge, overcoming the forces holding it together.
Let's break those down. Weakening the substrate. Solid rock seems strong.
Intact, fresh bedrock is strong. The mineral grains are held together by strong chemical bonds, but rocks rarely stay intact forever.
Tectonic forces.
Exactly. Tectonic stresses create joints fractures with no real movement and faults fractures where rocks have moved. This breaks the rock mass up, creates weaknesses.
And weathering.
Weathering is huge. Chemical weathering changes minerals into weaker ones. Physical weathering breaks rocks into smaller pieces. All this turns solid rock into weaker weathered rock and eventually into loose regolith. And regolith is held together by much weaker forces, friction, a bit of electrostatic attraction, maybe surface tension from water.
Like the difference between a rock sculpture and a sandcastle.
That's a great analogy from the source material, yeah. One is much easier to disrupt than the other. You look at some sandstone cliffs, like in Utah, and you can see they're just riddled with joints. That makes them way more prone to rockfalls.
Okay, so you have weakened material. Then you need the slope. What determines if a slope will fail or not?
It's basically a balancing act between the force pulling stuff downslope and the forces resisting that pull.
Gravity pulling down.
Well, specifically the component of gravity acting parallel to the slope. That's the driving force. The steeper the slope, the bigger this downslope force gets.
And resists it.
The resistance force. That includes the inherent strength of the material itself, those chemical bonds in rock, or friction between grains and soil. Also, how well the grains interlock, the effect of plant roots holding things together.
So it's downslope force versus resistance force.
Exactly. If the downslope force becomes greater than the resistance force, the slope fails. You get a mass movement. It's also helpful to think about the normal force, that's the part of gravity pushing the material directly into the slope perpendicular to it.
How does that matter?
More normal force generally means more friction, which increases the resistance. Think about trying to slide a book down a ramp. The steeper the ramp, the less the book pushes into the ramp, lower normal force relative to downslope force, and the easier it slides.
Okay. The sources mention the angle of repose. What's that?
The angle of repose. That's the steepest angle that a pile of loose, unconsolidated material like dry sand or gravel can maintain without collapsing.
So how steep can you pile sand before it slumps?
Pretty much. For typical dry sand, it's usually around 30 to 37 degrees. But for coarser, more angular stuff like gravel, it can be steeper, maybe up to 45 degrees.
Why the difference?
Shape and size. Angular grains have more friction between them, and they interlock better than smooth, rounded sand grains. You can see it if you just pour piles of different materials.
And what if there are weak layers inside the slope?
That's a huge factor. If you have a layer of, say, wet clay or silt, or maybe a zone of fractured rock from a fault, or weak sedimentary beds like shale, these act as zones of weakness.
Failure surface.
Potential failure surfaces, exactly. They dramatically reduce the overall resistance to sliding, and they're especially dangerous if they happen to dip downwards in the same direction as the land surface. Gravity has a much easier time pulling the overlying material down along that weak plane.
Any examples where that happened?
The 1959 Madison Canyon slide in Montana is a tragic one, triggered by an earthquake. But the failure happened along weak metamorphic foliation plains, basically, aligned minerals, creating weak zones that dipped parallel to the steep canyon wall, buried a whole campground. 28 people died.
It's terrible.
Yeah.
Okay, so we have weakened material on a slope, maybe with weak layers. What actually pulls the trigger? What sets it off?
Lots of things can act as triggers. Shocks and vibrations are big ones, earthquakes, obviously, but also big storms pounding a coast, even heavy trucks rumbling past, or blasting for construction.
How do vibrations trigger it?
They can momentarily overcome the friction holding particles together, or break weak bonds. And then there's liquefaction.
Liquefaction.
Yeah, this happens in wet, loose sediments like certain clays, quick clay, or saturated sand. When you shake them, the water pressure in the spaces between the grains increases suddenly.
Pushing the grains apart.
Exactly. It reduces the contact and friction between them, and the sediment loses all its strength. It basically behaves like a liquid and starts to flow. That massive slide and giant wave in Latuya Bay, Alaska in 1958, triggered by an earthquake, likely involving liquefaction and massive rock falls. You can even see liquefaction if you shake a tub of wet sand vigorously. It just turns to soup for a moment.
Okay, so shaking is a trigger. What about just changing things on the slope?
Absolutely. Changing the load, the steepness, or the support.
Load, like adding weight.
Yeah. Piling up fill for construction, putting buildings on a slope, or even just the ground getting saturated with water from heavy rain, all that adds weight increases the downslope force.
Which could push it past the breaking point.
Right. The Oso slide was preceded by a very wet period, and that huge Grove and Trace slide back in 1925 in Wyoming. Part of the story was heavy spring snowmelt saturating a thick sandstone layer that sat on top of weaker shale. The weight just became too much. Dammed the river, created a lake.
And making slopes steeper, like
Yeah.
from road cuts.
Yeah, cutting into the base of a slope for a road, or even natural river erosion steepening a valley wall that increases the downslope gravitational component, making failure more likely.
And removing support.
If you remove material from the bottom of a slope again, maybe river erosion, or waves cutting into a sea cliff, or human excavation, you take away the support holding up the material above. That can lead to collapse. Think of a sea cliff being undercut by waves eventually. The overhang fails.
Okay. And finally, the strength of the material itself can change over time.
Definitely. Weathering is a slow but relentless process. Breaking down rock, creating weaker minerals, that reduces strength over time.
What about plants? Vegetation?
Vegetation generally helps increase slope strength. Roots bind soil together, kind of like natural rebar, and plants absorb water, reducing saturation. So removing vegetation, deforestation, wildfires, clearing land makes slopes more vulnerable.
Like in Brazil, where deforestation led to more landslides.
That's a documented link, yes. And finally, water content itself has a really complex role.
How so? I thought more water always made it weaker.
Mostly, but not always. A tiny bit of water can actually create surface tension between grains, adding a little cohesion. Think damp sand for sand castles. But yeah, too much water is usually bad news.
Why?
It adds weight, like we said. It can lubricate potential failure surfaces. Crucially, it increases pore water pressure, pushing grains apart and reducing friction. That's the key to liquefaction. And some clays actually swell up and lose strength when they get wet. That quick clay slide in Norway, maybe triggered by blasting nearby, shows how sensitive some materials are to disturbance in water.
Okay, so putting it all together, where on Earth are these mass movements most common?
Well, the number one factor is relief. You need slopes. So mountainous regions, areas with deep river valleys, places carved by glaciers, coastal cliffs, anywhere with significant elevation changes is potentially susceptible.
When climate matters.
Hugely. Areas with lots of rain, especially seasonal heavy rain, are prone to saturation-triggered slides and flows. Deserts or high mountains might have less vegetation and more exposed rock, leading to more rockfalls due to freeze-thaw.
And the type of ground. Weak rock, loose sediment.
Absolutely critical. Areas with inherently weak materials are obviously at higher risk. That picture from Taiwan showing a hillside slumping after rain and an earthquake. Perfect illustration of multiple factors coming together.
The big picture, plate tectonics. Does that play a role?
A massive role. Plate tectonics is what builds mountains in the first place, creating the relief. Tectonic forces also fracture and fault the rocks, creating weaknesses. And of course, tectonics causes earthquakes, a major landslide trigger.
So, active mountain ranges.
Like the Southern Alps in New Zealand, they're being actively uplifted, mountains are steep, rocks are fractured, there are earthquakes and heavy rain. You get frequent mass movements there. It's a geologically dynamic place.
The sources use Southern California as a detailed example. Sounds like a perfect storm of factors there.
It really is, unfortunately. You've got the San Andreas Fault System, an active plate boundary. That means lots of fractured rock, pathways for water to weaken things, and even inherently weak rocks formed at the boundary itself.
And mountains are being pushed up.
Yes, there's compression, creating uplift, forming steep slopes, including coastal ones that get undercut by waves. Plus, frequent earthquakes shake everything loose.
And the climate.
Hot, dry summers mean sparse vegetation, prone to wildfires, which remove that vegetation. Then you get occasional intense winter rains that saturate the exposed ground.
And people living there add to the mix.
Urban development has definitely complicated things. Cutting into slopes for building, adding weight with houses and fill, changing drainage with irrigation and septic systems, it all affects slope stability.
Like that Portuguese bend slide near LA.
A classic case study, geologically weak layers dipping towards the sea. Then developers added fill material, people started watering lawns, using septic tanks, increased the water load and lubrication, resulted in this slow-moving but incredibly destructive slide that took out over 150 homes over time. You see similar slumps and slides up and down the California coast. It's an ongoing challenge.
Okay, so these things happen, and they can be devastating. What can we actually do about it? How do we protect ourselves? Can we predict them?
Protection starts with identifying the risk. Geologists and engineers are trained to spot the signs of potential trouble.
What kind of signs?
Looking for landforms from past events, those headscarps from old slumps, tilted trees, piles of old debris, bumpy or hummocky ground. These tell you the area has been unstable before.
And signs of current movement, even slow stuff.
Yeah, looking for active clues. Cracks in roads, buildings, pipes, fences or power lines getting weirdly tight or slack, new cracks or bulges appearing in the ground, wet spots or swamps appearing where they weren't before.
Can we measure this movement?
Oh, yes. We use sophisticated tools now. Satellite data, INSAR, ground-based laser surveys, LiDAR, tilt meters installed on the slope. They can detect movement down to millimeters.
And if movement is detected, or speeding up.
That's when warnings or evacuation orders might be issued, especially if there's a known trigger coming, like heavy rain forecasts or aftershocks expected. Predicting the exact timing is still incredibly hard, but monitoring helps assess the immediate danger.
Like at that Bingham Canyon mine. They predicted that big slide.
They did. They saw the signs, monitored the acceleration, and evacuated the area before the massive debris flow happened. A major success story for monitoring.
What about mapping the risk more broadly?
That's where landslide potential maps come in. They're usually made using computer analysis, geographic information systems, GIS.
What data goes into them?
All the factors we've discussed. Slope steepness, rock and soil types and strength, water saturation levels, orientation of faults and bedding planes, vegetation cover, rainfall patterns, potential for river or coastal erosion, earthquake probability.
Wow, a lot of variables.
It is. The computer models integrate all that data to create maps showing which areas have higher or lower relative risk for landslides. Very useful for planning and development.
Okay, so we can identify risky areas. Can we actually prevent landslides or lessen their impact?
We can certainly try using various engineering and land management techniques. It's often about either increasing the resistance forces or decreasing the driving forces.
Like planting trees.
Revegetation is a big one, yes. Especially plants with deep roots. They help bind the soil and soak up water. Simple but effective in many cases.
What about physically changing the slope?
Regrading is common. Basically making the slope less steep, reducing it below the angle of repose for that material. Terracing, cutting steps into the slope, also helps by reducing the overall angle and creating benches to catch falling debris.
And managing water. You said that's key.
Absolutely. Improving drainage is crucial. Installing pipes or trenches to carry water away, even pumping groundwater out in some cases, can lower the water table and increase the soil strength.
What about stopping erosion at the base, like rivers or waves undercutting?
Yeah, preventative measures there include diverting rivers away from the base of unstable slopes, building offshore breakwaters to reduce wave energy, or placing heavy riprap large boulders along riverbanks or coastlines to armor them against erosion.
And building structures, walls and things.
Definitely. Retaining walls are built to hold back unstable slopes. On road cuts, you often see chain link mesh or sprayed concrete called shotcrete, sometimes combined with long rock bolts drilled into the hillside to anchor loose rock. And in snowy mountains, you see avalanche sheds built over roads or railways.
What about controlled blasting? You mentioned that for snow.
Yeah, sometimes it's used carefully for unstable rock slopes too. Triggering smaller, manageable failures under controlled conditions can sometimes prevent a much larger, unexpected disaster later.
But all this prevention must cost a lot.
It does. There's always a cost-benefit analysis. Sometimes the best option is avoidance, not building in high-risk areas. But where that's not possible or practical, people and communities have to weigh the costs of prevention against the risks, consider insurance, and plan for potential aid if disaster strikes. It involves difficult choices.
So wrapping this all up, we've really dug into this idea of unsafe ground. Mass movement is this constant geological process driven by gravity.
Happening everywhere, all the time, at different speeds.
Yeah, from that slow creep to terrifyingly fast falls and flows on land and underwater. And it all comes down to that balance, doesn't it? Downslope forces versus resistance.
Influenced by so many things. The rock type, weathering, water, the slope angle, what's holding it up at the bottom.
And things like tectonics and climate setting the stage, creating the vulnerable spots.
But the good news is we do have ways to understand the risks, to monitor them, and often to take steps to mitigate them. It's where geology really meets engineering and public safety.
Which leaves us with a final thought for you, our listener. We know climate change is altering rainfall patterns, potentially making some areas wetter, and people continue to build and live in hilly or mountainous regions.
So the question becomes, how do we as communities, as individuals, best prepare for these ongoing, maybe even increasing risks from mass movements? It's worth thinking about your own local area. Are there risk maps available? What are the local planning considerations? Something to explore. We hope this deep dive covering the key ideas from our source material has given you a clearer picture of these powerful forces.